everyone, it's Judy Warner. Welcome to the first of a special podcast series developed in partnership with the Ecosystem podcast and Keysight University. In this first episode, I'm joined by Dr. Eric Bogatin, signal integrity guru and professor at CU Boulder. I'm also joined by his friend and protege, Dr. Tim Wang-Lee, who's a signal integrity application scientist at Keysight. Due to their history as professor and student, it makes for a really interesting conversation that I think you'll enjoy. Together, we're going to examine existing issues in the current SI design workflow and ways to better ensure an accurate correlation between simulation and measurement. We also discuss the important ways that EDA tools need to evolve to create that more efficient workflow and to help ensure accurate results. Before we hop into our conversation, make sure you go over and subscribe to Keysight University and also to the Ecosystem podcast community, where you'll get more technical resources and keep track of this series. Thanks again for joining. Now let's jump into our conversation with Dr. Eric Bogatin and Dr. Tim Wang-Lee. Hi, Eric. Hi, Tim. Thanks so much for joining in this fun conversation. Let's jump right in, and I want to ask you both, as way of introduction icebreaker, what is your favorite, each of you, one, two maybe, of your favorite memorable experiences as professor and PhD student around signal integrity at CU Boulder?
Okay, so I'm going to go first, so I get to embarrass Tim initially.
Okay.
So I'm not going to mention the comedy skit that Tim did at one of the restaurants nearby one evening. I still hear about it from my wife Susan. We both went to hear I'm not going to mention it. I know you've been practicing, and you are much better than you were.
Oh, so I'm basically a pro at this point.
I'm sure you are, and I can't wait to go to your next performance sometime. But that's not the story that I wanted to mention. Instead, I'm going to embarrass him another way. So he took. I was teaching the high-speed digital design class. And I think the first time I met you was when you took the class. And I don't remember if you were the TA for the class or you took it. You know, which one came first? But you were in the class, and I was doing a demo of ADS, and we were using that for a lot of the simulation examples. And I remember after the class, Tim was so excited with ADS. He said, "Oh my gosh, I love that tool. I can't imagine doing anything else in my life than using that tool and doing simulations with the ADS because it is so cool." And that was, I don't know, 3-4 years before he got involved with Keysight. But I made note of that, and he got a lot of chance to play with ADS. But this is one of those occasions, love at first sight. And it was based on that I tried to get him connected to Keysight and ADS, and look at him now. He's Mr.
Look
ADS.
At him now, Mr. ADS. Love it.
So love at first sight.
There we go. All right, Tim.
And just before you say anything, Tim, just know that I have the ability to retroactively change your grade. Let me be clear about that. So now you go.
All right, I'm gonna share two memories then. One sort of warm, the other one scary. The first one, I can still remember like it's yesterday afternoon that I was in the office with you. It was an interview for your research assistantship position, and we got talking about simulation and measurement, the dance between simulation and measurement. I brought up this branch line coupler project that I had worked on in undergrad, and I think that was the beginning of everything, because that full circle to my PhD thesis is about simulation and measurement. So that was my first warm memory. And the scary one is every single time Eric would say, "So what?" That always brings me down 2 notches. Doesn't matter how far I've gone in my research. The "so what" always brings me down to the ground and say, you know what, that's a good question. Eric always has a way to focus on the practicality and just to make sure that it has to be real. It has to be practical for people to use and to see, not just simulation. Results doesn't do much. It's the "so what." That's my two
My
memories.
my job here is done. I am that little voice in his ear every time he's doing something, whispering, "Okay, you've just explained this. So what?
So what?
What's the value of
Exactly.
it?
There
What
we
does it mean?"
go.
Okay,
So
my
what?
job
Gives me
here is done.
my
Okay.
chills.
Is this called mic drop moment? I can just leave now, and Tim can
Eric
continue.
leaves the rooms. Yeah. Yes. Well, that's fun. It's a real privilege to be with both of you SI engineers and the teacher and the student, and you both done amazing work in the field. So, for our audience, let's talk about signal integrity and the design workflow as it stands today. It's complex. The speeds are amazingly fast. We've talked about a tool, ADS, and there are other tools in the market. Let's talk about what the design flow looks like today and maybe where, well, let's just start there. Let's just talk about how the design workflow is today and how that flow is, and then we'll jump into asking you about where there's disconnects or bottlenecks in that process.
Okay, Tim, you want to go first, and then I'll give my opinion. Because
Okay,
you're more connected with the design community and designers out there.
well, I have to invoke what Eric always has to say about hope cannot be part of the design process. And that's why there are different parts of it that needs to be addressed. That's why I think Eric mentioned the virtual prototyping is very important, where you're creating what's in the real world in a digital sandbox situation. And there is also the compliance part that kind of merges the simulation and the measurement, because you want to make sure that once you've done designing, the design itself is measured and is compliant to the standard that's been drafted. And finally, back to the PhD thesis, it's the material property. There's so many things that can be different between measurement and simulation. You want to make sure that when you are simulating, when you're designing, you're getting the good starting point in your simulation.
You know, that is a really good point. And I have to say that's probably one of the most undervalued principles in simulation, that it's so easy to type in the numbers of, I'm going to use this geometry and correlate, and I'm going to use this dielectric constant. But when it comes to what you're just saying about simulation and measurement correlation, the number one biggest issue is, do you have the right material properties? And there's that disconnect you were talking about, Judy, between what you learn or what you get from the fab house and what you actually, or what the fab house tells you and what you actually get back from them, both in the geometry, cross-section information, and the material properties. That if you just blindly use those terms and plug them in, that's where you'll see differences between the measurement and simulation. And it is, if you want to get that good measurement simulation correlation, it's absolutely worth it to have some test structures on your board that you can use to independently back out the material properties and the geometrical cross-section. That's what Tim did in his PhD thesis. How can you do electrical test structures in order to back out what the dielectric thicknesses, line widths, conductor thickness, roughness, dielectric constant are. It is so important to get good measurement simulation correlation.
And to that point, it's real world. Like the dielectric, after it gets pressed out, is really this thick.
Yeah,
And,
you got to do it in situ.
You have to
so
do
you
it
know
in situ.
what the board is. Yeah.
If you just take all the ideals and you throw them in there, this used to happen to me a lot. I won't go down that rabbit hole. But the question always was, why is what I simulated different than the board you sent me? And I'm like, well, how long do you have? you know?
Yeah.
So, and I don't think engineers understood that the material properties side. So I think that's a really good answer.
Yeah.
Eric, do you have anything else you want to add to that before we jump into the pain points?
Yeah, I'll say one other comment. So, so Tim pointed out how valuable it is to have that kind of virtual prototype. It's easier, quicker to do quick turns in the design in the virtual prototype than in the physical prototype in the build it and test it cycles, and so doing the virtual simulation to help confirm design rules, help confirm the final post layout analysis is really important. I find there are always groups out there that I talk to that don't do simulation. They're at 10 gigabit, maybe even 15 gigabit. And they say, well, I'm going to use reference design, and I'm going to use, all the rules of thumb that I've seen and all the free stuff that's out there to design my product. And I am amazed at some groups can actually get successful 10 gigabit systems without doing any simulation. It's that one time that, they push the envelope a little bit. Or the way you add value to a reference platform is by customizing it in some way. And if you're just building a reference platform that somebody else has done, it's a commodity and you're not going to have as good profit margin. It's the customizing, doing something special, adding your own FPGA or your own ASIC in there or some other feature in there. And it only takes one time of screwing it up and not anticipating the problems that might have been uncovered in a simulation to have a 4 to 6 week delay time and then getting a board back that doesn't work, and it's really hard to debug. And so getting it right the first time, I find that companies that don't do simulation because it's too expensive or it's too hard to do, they're keeping their, just like Tim said earlier, they're keeping their fingers crossed and hoping the design will work. And they're using hope as part of the design process. And it only takes that one time for losing, 4 to 6 weeks or $10,000 or $20,000 of a board spin to have the design tool and the methodology pay for itself. And so you only have to get burned once in order to convince your management this is the right investment to make.
It's a very good point, by the way. Go ahead, Tim.
And just when Eric was talking, I had this phrase, expect the unexpected, in my head. Just it's with simulation that you can do that. When something is going to break, better it break in simulation than in real life, where, like Eric said, you had to spend 4 to 6 weeks. And like Judy, you mentioned, you have to really track down, is it the manufacturer? Is it the vendor? Is it the thickness that's different?
Is it the design?
Is it a design? So once it gets out there, it's broken. Everybody's going to start pointing fingers at each other. You can't really track down what's happening.
Mm-hmm.
Yeah.
And those board effects and not having that data, they're making decisions by data then, hopefully. And to your point, Eric, that I wanted to say is your point about people saying it's too expensive, which I've heard that over and over again, is like, have you done the math of how expensive it is to, say, spin a board 3 times? And they're like, well, it's just a prototype. I'm like, yeah, but if you do the math, and then if you're actually trying to get something to market or meet a deadline, really, it could go into the millions really quickly depending on the project. So I agree.
And it's the time. If everything is time to market and you lose 6 to 8 weeks of the market window, and that's where a lot of the profitability is in the early introduction.
Yeah, for sure. So pain points. We've talked about that's a big one. What existing pain points? Because we've already started this discussion around design workflow, right? And not going back to the beginning. If it was a linear process. So besides that, where are the pitfalls as it relates to design workflow, EDA tools, and engineering knowledge and situational awareness?
Yeah, I think it's probably 2 things. One is it is the complexity of a lot of the tools, and it is the it's that mismatch between the complexity of the tools and the expertise of the engineer, the user. And I always say that it's really easy. A lot of the tools, and I'm a big fan of ADS, but there are a lot of these tools that it's really easy to push the run button and get an answer. It's really hard to know, is that a good answer? Does that have artifacts? And have I screwed something up, or have I set it up correctly? And I mean this in the most loving way, and I'm not pointing fingers at you, Tim, but an awful lot. There are a lot of EDA vendors out there, a lot of application engineers,
Right.
and they are really skilled at knowing what buttons to push in their tool, not so skilled at how do I apply that to my customers' problems, or for that matter, like Tim alluded to earlier, ask that so
So
what
what?
question. It's the, okay, I've got an answer. It's okay, customer, it's your answer. Here's your answer. They don't understand how to interpret the so what. And it's left to the customer, which, yeah, that's their responsibility, but that requires quite a bit of experience and learning curve. And I think that it's that mismatch of the skill set of engineers and the skill set required to use the tools and to excel using the tools. And that's what, hey, here's my plug for our program at CU. We just introduced a professional master's program in high-speed digital engineering to help provide engineers that extra jump up and accelerating up the learning curve to be able to answer the so what kinds of questions.
Tim, what do you think?
Well, I have to add to what Eric was saying. As far as SI engineers goes, a good engineer press buttons, right? But a great SI engineer it knows what to expect and then how to interpret the results. I think that's two very different groups of engineers. And to answer Judy's question, the pain points from my side on Keysight, we see in the future there might be some future group collaboration. Like also, Judy, we had on another podcast talking about Altium 365, where not only is the engineers involved, is a marketing person, and also the vendor is going to be all in the same room. How do we work together? I think that's one big thing with each other. I think overall we're talking about design iteration. How do we really shorten that design cycle, get really quickly to time to market? And finally, the verification part with the right SI engineers and Eric's CU's program, I can vouch for. It's a lot better now. Now I've left.
Hey, it was pretty good before too.
It was
Wasn't
pretty good, but now it's even better.
That's a passive aggressive.
I
like Eric. I mean, Tim, I think you just burned yourself. Like
I just burned myself a little. It's like I came from the no. You can take that out in post.
It'll be on the cutting room floor.
Yes. But yeah, it's very the three steps. Working with each other. How do you empower yourself to learn more, and then how do you really shorten that design cycle productivity? Really.
right, and there are so many tools, so many different ways to solve it. You mentioned Altium. I know Siemens is taking a swing at it. And there's a lot of companies out there trying to solve the, which again, why I came up with the ecosystem is to get the ecosystem, get those silos down, right? So we know what our corollary stakeholders are up to. And we get it right the first time. And EDA tools are absolutely going to play a critical role because we can be in the digital sandbox, but we can also communicate across that. In some tools anyways, you can communicate and actually record when you made that decision, right? And go back and, oh yeah, that's why I did that. So it's not an easy thing. And I was talking to someone recently about millimeter wave and signal integrity recently, and that introduces a whole another level of sensitivity because the waves are so small. And so it feels like every time we take a step up in technology, we hit some more of these pain points. Tim, let's talk about what you're noticing, and Eric, what you're noticing, both from the industry side, the academic side, and from the EDA side, right? Let's look at this holistically. Where do you think EDA tools are going to go? We've mentioned a few players. Where do you think EDA tools need to go to make this better? Like, where are the bottlenecks? Where are we in areas where we're not yet where we need to be to make this work well? And no cheating, no AI conversation in this. So, in the world as it is today.
I'll take a stab at it. I would say in the future, I see all EDA vendors to be more collaborative. instead of having a zero-sum game mindset where we're all competing for the same customers, we should, I see that happening right now actually. We'll work together, and instead of trying to split one pie, we're gonna make many pies, right? That's the abundance mindset. We can help more people if we team up together and integrate our technology better. Then the technology will grow faster, and more people will be encouraged to simulate. And like the like the example Eric gave, people who are not simulating is because it's too expensive. Now, if that's the friction point, that is the blocker, right? If we can bring down that blocker, then we can achieve a world where people are using simulation to prevent these unexpected things to happen in manufacturing. And we can bring it back to everything going smoothly, and life quality will be better. And I might be naive whenever I get on the podcast and say the world will be a better place, but I guess I always end up there.
So what you're saying, Tim, is you're really working for world peace.
Yes, essentially.
Is this a beauty pageant or a webcast?
I can start dancing, but I don't want to see that.
Well, it sounds like you got your stand-up comedy shtick down, so maybe we should just transition now.
Eric will be the judge of that, huh?
I can't wait to come to your next comedy performance. Susan would be jealous if she wasn't there, though, so I'd have to drag her there. I want to add one other thing about where I think where EDA tools are going, and I think I kind of agree. I think what you're saying, Tim, is that as an EDA vendor, your competition isn't the other EDA vendors. It's the market space out there that doesn't simulate now, and so you just want to grow that market segment, and that'll grow the market for everybody. And I completely agree. I think there's a lot of folks that aren't simulating that will be. As speeds increase, your luck decreases, right, and you have to be simulating. I see another problem that is not, and I don't know that it's the EDA vendor's problem necessarily, but it's part of their holistic approach. The whole reason you simulate and do a virtual prototype is because you want to be able to anticipate how if I were to build this system as I envision it, here's how it's going to behave. And I can tweak a knob in my virtual prototype and see, here's how the real thing would behave. To do that, we talked before about how important it is to have the models for the interconnects, the dielectric properties, conductor, all that stuff. But equally important, and maybe even more so these days, is the models for the devices themselves, the transceivers. And if you look at like a DDR4 or 5 system, the parameter for one term, like the input gate capacitance for one of the DRAM receivers, is such a sensitive term, influencing the signal quality, because it's a multi-drop system, and you minimize the stubs, but you still have the input capacitance of the receiver sitting on that line that acts to cause reflections. That the quality of the simulation is only going to be as good as the quality of the model that you have for that device. And my fear is, if memory vendors understand how important the model is they have, in not whether someone's going to buy their product and the product's going to work, but how it's going to behave in a simulation, they may be gaming the system and providing models that don't necessarily match the real product, but will look good in a simulation and cut down on that input gate capacitance, for example. And when I've worked with a few vendors in helping them in their systems, and it's so clear that if you tweak that one knob, you can make a system, a DDR4 or 5 system, be a beautiful looking eyes, right, versus, oh crap, this isn't going to work. What am I going to do? And just by tweaking that one knob, and you're relying on that device vendor to give you an accurate model. And how do you know it's an accurate model? And that's just one component. You got the transceivers on all the FPGAs out there and all the ASICs that are, and these days, every my buddy Dave Dunham over at Molex, he says at 28 gigabits everything matters. And you cannot build a channel today at 20 gigabit where the eye is open. It's closed. The only way you open it is by the transceiver. That's what Don Telian keeps saying. Is it's all about the kind of the software, the firmware in the transceiver, setting the equalizations
The IBIS models.
the IBIS models, the AMI models.
AMI models, yeah.
It's all of the details in the quality. If you have
Right.
if you have a bad model and you don't know it, your simulation may be fantastic. You say, "Wow, this is great," but you're using a model that's a crappy model that doesn't match the real device. And there, I think one of the big gaps is, how does a user gain confidence in the quality of the model they're using from a vendor that is simulated or used as a model in a particular simulation tool? And that's a really tough problem. I think there are third parties out there that will do some kind of measurement simulation comparison of active drivers and create IBIS models. But I think the vendors of the ICs should take more responsibility in providing validation of the models that they create. And just a spiced IBIS correlation isn't necessarily good enough. You got to get real measurement simulation correlation. So I think that's a big gap that I don't see being addressed enough out there.
That's very true. That's very true. Especially, you mentioned ADS. ADS, Advanced Design System, is a software where you can pull in all the channel information and put in, like we're mentioning, the IBIS models and AMI models. And a lot of times, really, you can get a good eye, but is that eye real when you measure it? That's a different question.
And I don't think it's your fault. I mean, it's not about the simulation tool. It's about the vendor's model that they're running in the simulation tool. And who's accountable for that? How do you increase the confidence you have in that vendor's model? And so I think we should be collectively putting more pressure on the semiconductor vendors out there to prove to us, increase our confidence level that their models are accurate representation of the parts that we're getting.
That's definitely a big problem, and a lot of people have talked about it. Nobody's solved it exactly, but we've heard a lot of experts talk about, looking at data sheets with some level of cynicism, like don't trust data sheets straight out. And I think that, I don't know the answer. You two would know more than I, but I remember talking to a large semiconductor manufacturer whom shall not be named. And I said, "Why is this way?" And he said, "Honestly, part of it is because our lawyers get involved."
Oh,
and I'm like, "Oh wow, that's just a sad answer, right?" It's a protection of the corporation, so they're putting minimums and some of that, and
there's secret sauce.
There's, and I'm just like, that's just a bad answer for the industry. But I do know people, like you said, Eric. I have a friend, Mark Harris, that's working on that right now, and he's creating a site. It's not up yet, or I guess it's up yet, but it's not fully built out, called the Parts Playground, where he's simulating real world data and providing that. I think it's open source, so I know there's other people that'll do that. Okay, so these are some of the things we need to fix in tools, and everybody's coming at it different. From a business standpoint, I'm like you, Tim. I can be a little Pollyanna, like just everybody play together and the world will be at peace. And it's like, no, there's all these stakeholders with different agenda.
Yeah.
From a business standpoint, we just can't all jump in and play nice together. It's not quite obviously that simple, but I do see movement in that direction. Altium being one that we both know, that is working with companies like Keysight or Ansys or whatever, and trying to work cooperatively, right? So I think that is a good trend. All right, I'm going to let you guys go crazy. I'm going to ask you a question. I'm just going to step away from the microphone and let you go crazy. So these are some of the EDA tools, so that where they need to go, better communication, maybe cross-platform integration, being aware of that we actually have good models, and there's more we could unpack. But right now, all the talk is about AI and machine learning. And I'm positive this is going to come to bear on all our lives very quickly. So, where do you think EDAs could go or will go if we get AI involved? And will it help or hurt or do both?
I volunteer Eric.
Okay. So I'm watching this field very closely because it has a big impact on, our students and the field as well. And it's like so many aspects of technology that it's a double-edged sword. The good news is, boy, it can really increase the efficiency of a designer. That you can have a little, AI on your shoulder that is the expert system that's helping guide you and direct you. The danger is where the training input comes from upon which the neural net is created. And if it is based on information that is available on the internet or that is not parsed by an expert or a series of qualified, maybe peer-reviewed experts, the danger is that the AI will give you bad advice. And so I was at a conference with my buddy Todd Hubing. He's one of the world's experts in EMC, and he gave a talk about bad advice that you get on the internet. And I have a similar series of examples I pull out. He was talking about EMC. I have a similar one of SI and PI examples. And he had this long list of people that post information on the internet. Many times they're posting it there in order to get clickbacks to their company, and they don't get a grade on whether it's correct or not. And there is so much out there that we have this huge collection of myths and legends. And if the internet is used as the source of training materials, then we will get the myths and legends introduced, and we'll end up with mediocre engineers as the AI. And if the input is parsed by or curated by expert engineers, and it is continually evaluated and revised, then there's a chance that those AIs that are developed could be very useful in helping the design process. I'll offer one other concern I have. I interview students that go into college, and I am hearing more and more high school students, pretty sharp high school students, that are real familiar with machine learning and have developed, worked on machine learning algorithms and have developed training systems and are enamored with this idea of an AI can do anything if you just train it. And I'm hearing them tell me, why should I study physics? Why should I study electrical engineering? Because I'll just train an AI to do it. I don't have to know that. And my fear is maybe that's the case, but then you remove any sense of engineering judgment. And we are, when we create our own engineering judgment, we are basing that on our engineering intuition, our physics intuition, the root cause, the fundamental principles. And if it is just on a training algorithm of inputs leading to outputs, my fear is we're going to lose. It's going to be like COVID, to the 10th power, Googleplex of COVID, where we're going to lose generations of engineers, and we're going to end up with mediocre AI tools. So, a blessing and a curse.
Indeed, and I do have the same worry. It's a blessing and a curse. It's just too much power for young engineers to have in their hands, right? And Eric always says, and an expert is the person who has made all the mistakes. With an AI, assume that they all get correct information, right? The engineer itself, he or herself, doesn't get to make the mistakes. It doesn't register in their engineering brain. So back to Eric's point, well, we create all these bunch of mediocre engineers that can always ask AI for answers, but it's always that rule of thumb that you pull out in thin air that would impress people, right? And if you can quickly do it on the spot and do a quick check, that is not it's not gonna come from AI. Unless we're going crazy here, you get those crazy goggles, right? And then you can just pull it up with your hand. I don't know.
Yeah, it's
That's all. This is independent of Skynet
right.
and the
Well,
Matrix.
yes, I should put a disclaimer in here. All opinions of guest and host are not the responsibility of the podcast host or the podcast ecosystem or Keysight Technologies.
Yeah. So
Eric,
one last comment. Anybody that is interested in AI and is thinking about what it can do, there are the 3 movie series they have to watch. It's the Terminator series, The Matrix, and I, Robot with Will Smith.
Will Smith.
Because that was it's the same title as Isaac Asimov's book, completely different track, but it really talked about where, if the 3 laws are obeyed, where does that lead an AI to interpret what's best for humans?
Right.
So it is very scary.
3 of my favorite movies, sci-fi movies, and also I wrote a term paper in college about Isaac Asimov and the robot's 3 laws. So I really liked
Wow.
iRobot because it's about ethics and morals and judgment.
Yeah.
Right? It's these intangible sort of soft learning skills, these things that are distinctly human. So it's the human out of the loop is pretty scary stuff. I think there are great gains to be made, but with any technology, it can be used for good or evil, just like in the movies, right? Eric, I wanted to say something on the back to add to what both you and Tim have said, but you specifically about AI learning from the internet. Because I've been in marketing and I've worked for large companies that have a digital marketing force, I've seen that happen where I was the lone person saying, don't put anything that's not true out there. It's bad for the industry. It's bad for your customers. And they're like, but there'd be a separate human being that got rewarded for how many clicks, regardless of where those clicks went or what the information was. And it, content is king. And so from a marketing standpoint, I think we've sort of polluted the internet with bad ideas to get those short-term clicks. And that would also concern me greatly. Luckily, there's a lot of Dr. Eric Bogatin and Todd Hubing stuff out there too. So there's a lot of good
And Dr. Tim Wang-Lee's.
And Dr. Tim Wang-Lee. Wow.
Not enough these days, I have to say. Have to generate more content.
One last question for you both. In light of how EDA tools are evolving, the complexity, particularly of the signal integrity workflow, what is one piece of information, and I'm going to limit you to one, which is super not nice and cruel, but really, if there's one thing that you hear over and over and over again saying, why do I keep giving this piece of advice over and over again? What would that one thing be that we can leave with our audience before we go into the live chat?
Okay, so, I'm going to paraphrase Tim here. So I'm going to steal some of his thunder. So I'm going to say, always apply rule number 9. That is, anticipate before you simulate or measure, so that you know what to expect. And the second is, the other thing that he said is, always ask yourself, when you have a result, ask yourself, so what? What does it mean? How is that going to influence any decisions that I make? And the corollary to rule number 9 about anticipate before you simulate is, think of every consistency test. You always have to doubt yourself. Think of every consistency test you can do that will help you gain confidence in the result. I don't know that you can ever tell if you're right, but the more tests you do that show your result is consistent, and the tests are consistent with each other, the more confidence that you'll have in that result.
Good answer. Tim?
I agree. What he said.
I just
That's like saying, I agree with myself.
Yeah.
Well, I think it's time, gentlemen, thank you so much for this fun, enlightening, and interesting conversation. I trust it'll help everybody that is watching.
And Judy, thanks so much. It's been a pleasure. And Tim, always good to see you again. Can't wait for that comedy show.
Thank you, Judy. Thank you, Eric.